equations are much simpler than you think because we done most of the work through that floating base equation. So next is foot strike. Okay, this is really going to be quick deriving the equations because we've already derived them for single stance. So we derive this equation, right? Plus J transpose C1 P C1 plus J transpose C2 P C2. Okay, this is from, I'll write SS for single stance. Now, in order to find the foot strike equation, the foot strike occurs when the swing leg hits the ground, and then it becomes the leg which is going to be anchored to the ground, and the other leg is free to move, right? So that's sort of the case where there's a plastic collision. In order to find the foot strike equation, so this is similar to the equations for the bouncing ball when the ball bounces. When something bounces, collides, there's an impulse, and that impulse is responsible to cause that plastic collision. So what we can do is we can integrate this equation for that tiny instant during foot strike. So that instant goes from, I'm just going to make something up, t negative to t positive. Okay. So that t negative, t positive means it's for a very, very short time. Okay. To t positive is a really short time or instance. Okay, now what we can do is we can think what's going to happen when these equations are integrated. So first of all, when you have these forces like Coriolis forces and gravity forces, what's sitting here is Coriolis, centripetal, and gravity. When there are impulses, there are large forces acting for a very brief amount of time. When you integrate these terms, I forgot to put the dt. When you integrate the Coriolis and centripetal gravity terms, the contribution of this to the impulse is zero because those forces are finite and impulses are infinite. Okay, so that goes to zero. Now, when the front foot hits the ground, let's just draw this caricature here again. This is C1, and then the other leg is C2. So this foot is going to hit the ground. So we make an assumption here that is when the front foot hits the ground, there's a large impulse here, or there's an impulse here on the front, on the leading foot, and there's almost zero impulse on the rear leg. That's because the foot C1 is going to be lifted up. Okay, so what we can effectively do is we can say that this is practically zero because we make the assumption that that foot is going to be lifted up, and then this is not equal to zero. So the only two parts which remain in the equation are the first and the second. So let's just integrate this now. So if we integrate this, we get mq, and I'm going to integrate q double dot, and that's going to be q dot. The integral of q double dot, which is the acceleration, is going to be the velocity. I'm going to put q dot positive to indicate the instant after foot strike, or t plus, q dot negative. Okay, and I can do that because this sort of pops out. It basically is the M matrix is a function of angles. Okay, and for that brief instant when that foot hits the ground, the angles are not going to see any change. The angles are not going to change. It's only the velocity and the acceleration which will change. So the q dot will change, right? That's why we can take the mass matrix out and keep the q dot plus and q dot minus. Okay, so that's the first part. And the second part is basically this impulse. So JC2 transpose. Again, JC2 is a matrix consisting of only angles. It doesn't have velocities in it. So you can pull it out and you're left with pc2 dt t minus t positive, which you can call as the impulse on the swing leg, this one. So let's give it a name. Let's call that, I guess you can call it IC2. Okay, which is IC2. Okay, so that is basically the equations for Footstrike. However, we're missing one ingredient equation. So when we write this equation, it turns out that we'll have too many unknowns than number of equations, and that's because q dot plus positive. So q dot negative is the velocity before Footstrike. We know the velocities before Footstrike. We do not know the velocities after Footstrike. Q dot positive is x dot positive, y dot positive, theta 1 dot positive, theta 2 dot positive. Okay, so those are the unknowns. IC2 has IC2 along x, IC2 along y are also unknowns. Okay, so here we have four equations. There are four equations because the mass matrix has four elements. So we have four equations and six unknowns. So we can clearly not solve for the, there are too many unknowns than equations. It turns out there are two more equations which we've totally ignored. The last equation which we actually ignored is the fact that this point C2 is stationary. It's not going to move, right? Because C2 was swinging in the air, but when the Footstrike took place, C2 became stationary. And so that condition is that velocity of C2 is 0. But what is the velocity of C2? It can be written in terms of Jacobian. So the velocity of C2 is Jacobian of C2 times, and this is basically the velocity after Footstrike, right? Not before. Before it was not 0. After Footstrike it's 0. So it's JC2 positive times Q dot positive, and that's equal to 0. So this is basically two more equations. So now we have 4 plus 2, 6 equations, and we have 6 unknowns, and we can solve it. Let me just write down what this matrix will look like. So I have written down so far mq dot positive minus q dot negative equals jc1 impulse, jc2 impulse c2 transpose, and then I wrote down jc2 transpose q dot positive equals 0. Okay, so what I can do now is I can collect these terms. This I can write down as, we'll rewrite the first equation as mq dot positive minus jc2 transpose ic2 equals mq q dot negative. That is, I'm only putting all the known terms on one side and unknowns on the other side. So now I can rewrite one as m minus jc2 transpose q dot positive ic2, and then the second part will have jc2, so it will be jc2 transpose, and since there's nothing which for impulse will be 0, equals jc, sorry, this will be mq q dot negative and 0. Okay, so this is the equation for Footstrike. It's very, very simple. Once you know the mass matrix, which you got from the single stance, you know the Jacobian because you know the position of C2. That simply is the velocity after, just before Footstrike. You can find the velocities after Footstrike and also the impulse. Okay, so if I to give me something like this, so note that this is an algebraic equation. Okay, which means that you don't have to integrate anything, right? It just tells you what happens after Footstrike, the positive, depending on the speeds before Footstrike. So that is telling you the velocities, because q dot The derivative is the velocities. What about the angles? Okay, so I'm going to draw a few caricatures which will help me to find the angles before and after foot strikes. Now, first of all, the angles will not change, okay? And that will be reflected in two of the figures. But then what we do is, instead of modeling a stance leg, um, taking one leg as the stance leg, writing the equations, taking the other leg as stance leg, writing the equations, and having two sets of equations corresponding to two legs being on the ground, we just write one set of equations and sort of switch the convention from one being the stance to it being the swing leg and so on. And that just helps us to write lesser number of equations. But what I'm doing here need not be done, but you could potentially do it to save uh, bookkeeping and so on. If you have two legs which are dissimilar, then you cannot do what I'm trying to do here. Okay, so let's see what I'm doing. First of all, this is the instant before collision, and there's a ramp. And so this is the trailing leg, let's say C1. This is the front leg, which now is just about to strike the ground. The angles are such that we have, this is theta 1, negative indicating that's the angle made by the stance leg, okay, before foot strike with the vertical, and that has to be negative because that's how our convention is. And then the angle made by the stance leg with the swing leg, which is this, is theta 2 with a positive sign, sorry, theta 2 with a negative sign. It's just how that's how the convention we've taken. Now if you look at the instant after foot strike, which is plus, you have uh, nothing will change really. It'll just simply be the same thing, same figure. The angles are also going to be the same. So this is still theta 1 positive. Oh, sorry, it's positive because it's after foot strike, but then there's no reason to believe these will be different. They're the same. And then the same thing for this one. It's going to be theta 2 positive. Okay, now here's where things will become slightly different, which is now you want to integrate the equations. So this is C2 and this is C1. Okay, now you want to integrate the equations and you have the option of writing the equations all over again, assuming C2 is the stance leg. Do the same thing which I did for C1 as the stance leg, write the single stance equations, and then you'll have a foot strike condition and so on. So that is one way to do it, which is you write a different set of equations for C1 as a stance leg and C2 as a stance leg. But that's doing double work because we know that the two legs are similar. And so instead of doing that, what we'll do is we'll switch the legs right here. So we'll make, just move this a little bit around. So instead of writing the equations all over again, we'll just switch the legs. What I mean by that is we'll make C2 as C1 and C1 as C2. So we draw the same figure, with put C1 as uh, the front leg and C2 as the trailing leg. Note that we switched. And to keep the convention work for us, what we need to do is now change this angle made by C1. We always measure the angle made by the stance leg with the vertical. So this is going to be a new theta 1 because uh, the angle made by, we always keep a track of the absolute angle between the stance leg and the vertical. And then for theta 2, we would have this angle. Okay, note that I dropped the theta 1 and theta 2 because now these equations are for single stance again. Okay, so what we need to do is we need to have this switching condition, which we can now observe just by looking at the figure. So first thing to note is that theta 2, which is this, is negative of theta 2 positive, right? And that's because if you look at the way this arrow is, it's pointing to clockwise, and this arrow is pointing counterclockwise. So we need to switch the theta 2. Similarly, if you want to find the velocity, you'll have to switch the velocity. So omega 2 is minus omega 2 positive. So that's one set of equations. Okay, let me delete this for a second. Okay, next we need to find a switching condition for theta 1. Okay, for that, what we do is we note that this is the angle made by the stance leg with the vertical, so that's theta 1. And then we try to see the same angle on this side, so it's basically going to be this angle. So for that, what we need to do is we need to take theta 2 positive, which is this way, and then subtract from it theta 1. So minus whatever angle is here, which is theta 1 positive. So it is a negative. So it's theta 2 plus theta 1. Sorry, I'll switch it, theta 1 plus theta 2 positive. And so if you want to find omega 1, it's going to be omega 1 positive plus omega 2 positive. Okay, so these two conditions give you what happens when you switch the legs. It gives you what theta 2 is and omega 2 is, and then given theta 2, which you can put, given theta 1 positive and theta 2, you can also find theta 1 and omega 1, and then your switch is complete, and then you can then again and simulate in single stance and keep doing it. Okay, so that's one thing. Now, the last thing which is left before we finish the derivation is detecting the ground. Third one, detect ground. Okay, so when will you stop the integration? So remember that we did the bouncing ball example where we said that the ball will reverse velocity when the height is equal to 0. That's when the ball touches the ground. When it comes to the walker, we actually don't need to put the slope here. We can just put a horizontal line just because our axes are along the ramp. Okay, so this also makes it easier to understand. So let's say this is C1 and this is C2. Okay, now we need to find a condition on when the C2 touches the ground. So for that, what you can do is you can observe that we have minus theta 1 and then theta 2 negative. And so, or rather, let me just put theta 1 and theta 2. So one way of doing this, and this is how people do it, is they find the height. So they find the position of C2 with respect to C1, okay? And that's the height of swing leg, which is C2 with respect to stance leg, C1, okay? And whenever this value is equal to 0, that means that YC2 is same as YC1, you can basically figure out that it is basically, you need to stop the integrations. This is where you detect the ground. Okay, so that's what they'll do normally. In this case, what you can do actually is when C2 is contacting the ground, and also given that these two angles, these two lines are the same length because they're the leg lengths, we'll see that this angle should be the same as this angle, okay, or it is a isosceles triangle. So in this case, you can see that theta 1, which is this angle, equals theta 2 minus theta 1. Okay, in other words, theta 2 is twice theta 1. So this is the condition on the when we detect the ground. It's much simpler than doing this thing, but if you have a complicated robot with feet and all, you might want to do yc2 minus yc1 equal to 0. Okay, so with that, um, okay, so before I go to the derivation, there is one issue though when you do this detecting the ground contact. It turns out that this condition is met two times in the walking cycle. Theta 2 equals to theta 1 is met two times. Okay, and that once it's met when the legs are nearly vertical. When legs are nearly vertical, theta 2 will be equal to theta 1, and this is where you don't want the integration to stop, because clearly that's not when when there's a step length or there's a finite step length. And then there will be the normal condition which you want to detect, which is basically this one, which I just drew. Okay, so you don't want to detect this one, so you don't want this to be detected, and you want this to be detected. So in the code, uh, I'll have a code called collision.m, which is an event in ODE 4.5, where I will show you how exactly to deal with this situation, how to take care of this situation where you avoid stopping the integration here, but you stop the integration there. It's as simple as saying that if this is true, and if theta 1 is less than some value, let's say minus 0.05, then you say you just don't stop the integration, you just continue integration. So then what will say, what will happen is it will continue integration till it stops here. And this will become clear when I show you the code. Okay, so what I'm going to do next is show you the derivation, and then I will try to actually spend some time deriving, so